Previously, we have introduced the concept of reinforced concrete member subjected to torsional load. We mentioned about the importance of the reinforcement, which include the longitudinal reinforcement and the link in controlling the torsional crack. We also mentioned about the derivations of the amount of reinforcement required is done on the basis of an equivalent thin wall box section using an imaginary truss model where the longitudinal reinforcement and the link serve to take the tensile stress in the member, whereas the compressive strength of the concrete contribute in the compressive resistance. It was mentioned that the failure of the member when subjected to the torsional load can occur when either the longitudinal reinforcement, the link, or the concrete fails. Any one of them fail, the member would have failed. So far, we have discussed about the derivations process for the longitudinal reinforcement as well as the torsional link. We mentioned that the calculated amount of the torsional reinforcement required are to be added up with the existing design, catering for the bending moment as well as the shear load. You will need to add both of them up in order to get the total amount of reinforcement before finalizing the design in terms of the detailings of the reinforcement. The principle is this. By summing up the total reinforcement from the what is required in the basic design plus the torsional reinforcement, it is to cater for the most critical situations where both the moment and the torsional loads are at its maximum, or both the shear loads and the torsional loads are at its maximum. There are also requirements in terms of how you can space the reinforcement, not more than 350. And then in terms of the link, make sure you use the fully anchored closed link, and the spacing should not be greater than the peripheral of the equivalent box sections divided by 8. Now, if your initial design for the shear link are not using this full anchored closed link, you should change it to this. And if your initial design, the spacing between the link for the shear load exceeding this limit, make sure you revise the spacing between the link. What you see here, we have done the derivations of the longitudinal bar and the link. We have not mentioned about checking if the compressive strength of the concrete is exceeded, knowing the fact that the failure of a member subjected to torsion can be due to the failure of the longitudinal bar or the link or the compressive concrete. So in this video, we're going to look into the maximum resistance given by the concrete. You may refer to this slide. Let me first explain the diagram first before we look into the derivation process. This represents the cross-sectional view of a member subjected to torsion. A thin wall box section is assumed, where you need to calculate the effective width and there will be shear flow, resisting the torsional force. Now, we look on the side view of the model, representing this side here. This shear flow is actually the shear force per unit length. To get the total vertical force acting upward, you will need to multiply the shear flow with the effective height. Bear in mind that this effective height should not be confused with the gross height of the section. Because we are assuming the shear flow is developing within the center axis of the effective thickness. By referring to the diagram here, you know that the effective height here is calculated on the basis of the central axis of the effective thickness. You're going to bring this height here. And then the shear force, it will be the shear flow times the effective height. And then we're going to look into the imaginary truss model. You have the reinforcement, you have the link, and you have the compressive strut. It behaves like a truss model. The reinforcement will contribute the tensile resistance, and the diagonal strut will contribute the compression. Now you need to do some trigonometry derivations. Draw two parallel lines along the angle for the compressive strut. Assuming this angle is equals to theta. Extend the parallel line and then draw one vertical line downwards. This height here, it will be equivalent to this height. And this angle here, it will be this angle. What you see here, there is a right angle triangle. With this edge as the Pythagoras, now you can play around with the sine cos theta. Cos theta here, it will be equals to this edge divided by this edge. Rearrange the formula. You will get this edge equals to h times cos theta. Having this being brought into the right angle triangle here, you have an angle theta here. Now you know this horizontal component here equals to h cos theta. Now you see this vertical forces here, based on the free body diagram, it will be resisted by this force, so that the sigma Fy will be equals to 0. This form a right angle triangle here, with the vertical component equals to QH, which is this force, and then horizontal component equals to h cos theta, which is this width. Based on the principles of trigonometry, sine theta, it will be equals to QH divided by this Pythagoras h, assuming this length is equals to x first. Rearrange the formula. Bring sine theta to one side and bring x to the other side. Now you know this length, it will be equals to QH divided by sine theta, which is this one. Now the concrete regions taking the compression, it will be this region. If you want to determine the stress acting on this region, imagine this is a plane. The stress in the compressive strut, it will be equals to the forces divided by the area. Let us first deal with the force. This is the force that we have calculated just now. QH divided by sine theta. As for the area, we are talking about this width times the effective thickness of the section, since we are referring to this section only. That's why you get the effective thickness times h cos theta. Now, if you put these two formulas together to get the stress in the compressive strut, the h here will cancel out each other. It finally emerged into this formula, which is in the functions of the shear flow, divided by the effective thickness, and you have sine theta and cos theta. This represents the compressive stress taken by the concrete within this section. However, the concrete has its limit. Its strength is the FCK. When the compressive stress is higher than its strength, the concrete will crush. We want to avoid that. Make sure the concrete do not crush in order to ensure the integrity of this hollow section. And then don't forget about the partial factor of safety for the concrete. The partial factor of safety for the concrete is equals to 1.5 as stated in the Eurocode 2. Therefore, the compressive stress here, it will be limited by FCK divided by 1.5. Having this established, then we need to determine the maximum shear flow, which is related to the maximum torque that you can apply onto the member based on the strength limit here. We have discussed about this formula previously, as you've seen this in the derivations of the longitudinal reinforcement and also the torsional link. Substitute the Q here, where you're going to have these 2 times the effective area being brought to the opposite. You will get this formula. Now you rearrange the formula here, leaving the maximum torsional strength on one side and the rest on the other side. Bring this whole thing to the opposite. You have 2 numbers here, you merge them. Use 2 divided by 1.5, you get 1.33. The rest, it will be rearrangements of the symbols. Next, use the trigonometry to rewrite the formula. And then you get the fundamental formula for the maximum torque applied onto the member. Now, Eurocode tends to be slightly more conservative. There is an additional strength reduction factor, which is this new one. This strength reduction factors formulas is given here, which is in the functions of FCK, leaving you the final formulas to determine the maximum torsional force that can act onto a member equals to this. This will represent a very important step for you to design a member subjected to torsion. The concept, it will be quite similar to the design for the shear reinforcement. You must first make sure that the maximum torsional force not being exceeded. Only then you proceed with the calculations of the longitudinal reinforcement and then the torsional link. Now, in the case that you found that this maximum torsional force is being exceeded, the implications, it will be the member will undergo brittle failure due to the torsional force. Why is it so? Because the failure is due to the crushing of the concrete when the compressive strength of the concrete is exceeded. Concrete failure, it will be brittle, and you do not wish to have this to happen. So in the case that when you check for the maximum torsional force, you realize that the maximum torsional force has been exceeded, you will need to redesign the section. This must pass first before you design for the reinforcement.